Imagine spending 50 hours manually fixing a shattered data pipeline just because someone upstream changed a single column name. What if that pipeline could detect the break, write its own fix, and, well, completely heal itself in under 60 seconds? Welcome to this deep dive. Today we are dissecting the Agentic ETL solution.
Right, which is essentially an autonomous nervous system for your data infrastructure. Let's look at heading 1, auto-healing data pipelines. This is a necessary structural evolution.
So summarizing the intent here, this is about operational autonomy.
Exactly. Version 1.0.0 is fully production ready right now. Operationally, it maintains 99.9% throughput and the latency increase is less than 5 milliseconds to the pipeline.
Which brings us to the baseline problem under heading 2. Legacy monolithic ETL shatters when schemas change. Legacy systems are basically brittle glass pipes, one upstream anomaly, and you get a systemic downstream fracture.
Precisely. When those monoliths break, single jobs just fail completely. You hit zero business continuity during the transition.
And engineering teams end up absorbing that burden.
Right, losing over 50 hours per manual remediation incident.
So moving to heading 3, the evolutionary leap to agentic ETL. We have to question if that operational burnout can actually be automated away.
The metrics indicate it can. Detection time drops from days to between 0 and 5 seconds.
And the remediation.
That executes in under 60 seconds. For common schema changes, you literally achieve zero manual intervention.
That requires a serious orchestration ecosystem. Heading 4 covers this, a complete orchestration ecosystem ready for deployment. What exactly is the structural footprint here?
The central engine is surprisingly lean, over 1,200 lines of asynchronous Python. It connects to a React and WebSocket command dashboard for real-time visibility.
And it handles the CI/CD pipeline directly.
Yes, it integrates with Azure DevOps for automated pull requests while managing an infrastructure baseline of over 40 dependencies.
I want to challenge that recovery timeline under heading 5, achieving business continuity in under 60 seconds. We are talking about a 4-node multi-agent handoff. Walk me through the mechanics.
It is a highly synchronized sequence. First, the Watcher agent detects the schema break in 0 to 5 seconds.
Then it hands off to the LLM reasoning agent.
Exactly, which analyzes the risk profile in 1 to 2 seconds. The Lineage Agent then maps the downstream dependencies in 2 to 5 seconds.
Leaving the remainder of the minute for the actual fix.
Right. The Remediation Agent drafts and applies the fix in 10 to 30 seconds.
But executing automated code adjustments directly in a live environment sounds incredibly risky. Heading 6 addresses this, the dual action mechanics of a virtual patch. How do we avoid deploying a bigger disaster at machine speed?
That is where the virtual patch comes in. The system immediately applies a temporary mitigation to bypass the break, keeping the data flowing with zero disruption.
And for the permanent resolution.
It does not just overwrite code blindly. It automatically generates a review-ready Azure DevOps pull request, assigns specific engineering reviewers, and links the work items. You retain final control.
That significantly lowers the risk profile. Let's look at heading 7, uncompromising system performance and reliability. What are the empirical metrics?
Detection accuracy exceeds 99% through persistent real-time polling, meaning zero false negatives. It predicts breaking changes with roughly 95% accuracy.
And the total execution velocity?
Consistently clocks between 20 and 60 seconds, from detection to full business continuity.
Moving to heading 8, built-in enterprise security and automated compliance. Automated data movement triggers strict regulatory scrutiny. How does it hold up?
The base layer automatically generates a 100% complete audit trail. This satisfies SOX compliance for tracking schema changes.
Does it cover healthcare and privacy frameworks?
Yes, it ensures IPA readiness by maintaining complete lineage visibility, supports GDPR through automated retention policies, and perfectly aligns with NIST incident response frameworks.
From a financial perspective, we have heading 9, the return on automation equation. What is the justification for implementation?
Well, mean time to recovery plummets from 20 minutes to just 1 minute. Factor in the avoided downtime and the elimination of manual audit logging, and you generate a conservative first-year ROI of over $200,000.
Let's transition to the chronological integration roadmap. Heading 10 is the 5 phases to production deployment. What is the schedule?
Phase 1 establishes the DEV foundation in weeks 1 and 2. Phase 2 integrates the CI/CD pipelines in weeks 3 and 4.
Then standing up the dashboard.
Right, Phase 3 by week 5. Phase 4 pushes to production between weeks 6 and 8. Finally, week 9 and beyond focus on optimization and LLM enhancements.
But what is the infrastructure baseline required before initiating Phase 1? That brings us to heading 11, deployment readiness requirements.
Prerequisite readiness demands a Python 3.11 plus environment, establish connectivity to Oracle or SQL Server databases, and verified .env credentials.
I assume chaos engineering protocols are necessary too.
Absolutely, you need fully validated chaos engineering protocols to ensure rollback procedures function correctly.
Finally, heading 12, immediate actions to initiate the paradigm shift. What are the tactical next steps for your engineering teams today?
First, review the core architecture logic in the agent.system.py file. Next, execute the local DEV demo to witness that 60-second recovery process firsthand.
And audit the current configurations against those prerequisites we just discussed.
Exactly. Assess your environment to ensure deployment readiness.
That provides a very clear tactical roadmap. We will conclude with a final thought for you to consider as you review your own infrastructure. If a pipeline can autonomously heal itself, map its own lineage, and author its own pull requests, at what point does data engineering shift entirely from writing code to simply governing the behavioral boundaries of AI agents?